Okay, so this is the notes for Honors Math 3, Unit 11, Objective 2, and this is the definition of the derivative. So something that we already know back from our, Math 1 or Algebra 1 days is we have done slope of secant line. So if we take a look at the slope of a secant line, we know in general it is just the change in y over the change in x. So if we have a graph that is, I'm just going to draw a parabola graph. So let's say we have a parabola graph here. We would have to have 2 points, right? So wherever those 2 points are, say there's one on the left branch, one on the right branch. And then when I draw a line through that parabola, through 2 points, I am drawing a secant line. So this is a graph of a secant line because I am working with 2 points that intersect the graph. So a secant line can intersect more than 2 points on a given graph, but when we are working with 2 given points, that's when we are working with a secant line. And so how I would go about trying to find the slope of that secant line is I would find the change in y and the change in x, right? So rise over run, that's something you probably have heard. So delta x meaning how far to the left are we going, and then delta y, how far up or down we're going. And so that's how I would find the slope of the secant line. So I would work with 2 points on the function, whatever that might be, in this case a parabola. And then with those 2 points, I would find their delta y, the rise, and delta x. And then how we do that is we subtract the y values, right? Because that gives us distance when we subtract. And then I would subtract the x values, and that would give me that value as well. Okay, so that's like our old way, right? That's how we would find slope of a secant line. So what calculus does is it defines our tangent line with slope n, okay? So if we have a function that is defined on an open interval containing c, so open interval meaning we're not looking at the endpoints, and then this definition right here, so this is our limit, right? We're taking a limit, and we look at the change in y, so that's what this top piece is, the change in y over the change in x. So in particular, we say, okay, well, what happens if that change of x goes to 0, right? That's what the limit is telling us. So this limit right here is saying, well, what if delta x approaches 0? Well, we know it can't actually be 0, because if it was 0, then we would be dividing by 0. But what if it approaches 0? And that's when we create our tangent line. So when we take a look at this delta x distance here, if it shrinks and becomes smaller and smaller, then this point would slide towards the other one, or vice versa, 2 points becoming 1. And why is it? Because our change in x approaches 0. So that little limit component there, so if that limit exists, then the line passing through c f of c with slope m is a tangent line to the graph of f at the point c f of c. So if I were to take this dot right here, right, so we're going to say that is at c. So then that point that I have there, so c comma f of c, okay, so this is our f of x graph, that is what we call the point of tangency. Okay, so that is our point of tangency. And then that slope is given by that limit definition. So they're saying you have some sort of y value, f of c plus delta x minus f of c, and you're going to find the difference between them, and then you're going to have some sort of delta x, and you're going to take that delta x and approach 0. And then that's going to give you the slope of a tangent line. I'm just going to do a little subscript there for t for tangent, okay? So this would be a tangent line here. All right, so where is that whole c plus delta x, that sort of thing? So really what that is doing is it's having like a secondary point wherever that is. And so we would usually say that delta x is really, really tiny. So we're going to say, let's pretend that that is our delta x value. And so if we take a look at this distance right here, so this would be delta, actually let me go to the other side, because I'm going to need that space for the other problem, or the other section. And let me zoom in just a tiny bit here for me. Okay, so I'm just going to move to the other side of the graph. Okay, so let's say this dot here, so I'm moving over here, and let's give this a distance of delta x. So if delta x becomes smaller, right, because it has to approach 0, then this dot that I drew here should actually be a little bit closer, right? And then are we still approaching 0? Of course we are, right? Because that's what the limit is telling us to do, but we're not very close to 0. So that dot keeps sliding, right? And it keeps getting closer and closer to that point of tangency. And every time it does, that rise over run. So if we look at this original one, so we have that delta y, whatever that is, and we have that delta x. And so then we get a little bit closer, right? And then we just keep shrinking, right? That triangle, that slope triangle just keeps getting smaller and smaller until delta x approaches 0. And so this f of c plus delta x is just talking about that original y value, right? So wherever that original y value is. So in this particular case right here, that would be f of c plus delta x because we moved over delta x, okay? So sometimes that can be really difficult to understand, but that is okay because you will work with the definition of the tangent line again, next year. But it is important to kind of grasp the algebra piece of it because you're going to be working with it a lot next year, and so it's good for us to, practice that component. All right, and then let's go ahead and take a look at this other picture over here that we have. So again, this left line that I have here, this would be a secant line, right? And why is it a secant line? Because we are working with 2 points on the function, right? 2 points on the function. So again, a secant line doesn't mean that it can only intersect the function twice. It can actually intersect it lots of times, but we're only working with 2 points on that particular line. And so if I look at the secant line, the slope of that, it would just be delta y over delta x. And then we don't worry about the points being close to each other at all, right? So a secant line, again, one more time, is when we're dealing with 2 points on the function to find slope, delta y over delta x. But tangent line, we're dealing with only 1 point, right? We're dealing with 1 point on the function to deal with slope. And so that's where that calculus piece comes in, because how do you find slope given 1 point, right? We know how to do it with 2, but how do we do it with 1 point? Okay, so we will get to that shortly. All right, so this next component here, so the actual definition of the derivative. I certainly don't want to be in gray highlight. So definition of the derivative. So it is that same definition that we had before. So we're going to be taking that limit as delta x approaches 0. And we're going to find some sort of change in y value over the change in x, right? So that's pretty easy, right? We know how to find the change in y, and we certainly know how to find the change in x. And then all we have to do when we do that is take that limit to 0. And so the notation we use for derivative, okay, so that notation we use for derivative. And so that's what this right here is, right? So that is the notation we use for derivative. Okay, are the most common. There's going to be lots of them we'll talk about here in just a little bit. So whenever we are talking about the derivative, that is the symbols that we will use. And so when we read this out loud, so when this is read, we will read it as f, and then that kind of apostrophe there is prime, just like we did reference angle, right? Theta prime for reference angle. So f prime and then of x. So not multiplying, right? So f prime is not multiplying x. That is just saying it is a function of x. All right, so there is our definition of the derivative, and you're going to do a lot of derivatives next year. This is just our first introduction into derivatives this year. So you will get used to them and you will learn to become very proficient in them. Might be a little rocky this year, especially with distance learning, but you will make do. Okay. All right. So we have this alternate form of the derivative. So this is just showing this to you. We actually are not going to be working with this this year, but there is more than one way to calculate the derivative with limits, and you will do this next year. But just so that you know, there is more than one way to work or to define our derivatives. So here is just a second one. Okay, so the one that we again will be using is the one above. All right, so just like we had our limits, so we know one-sided limits must exist, right? And these one-sided limits are called derivatives from the left and from the right. So we do have our one-sided limits, right? And when we do our one-sided limits, as a reminder, and that looks something like the limit as x approaches, say 1 from the right, yeah, of whatever our function is. And so we can also define one-sided derivatives as well, okay? All right, so we talked about other notation, right? So notation for derivatives. So the ones that are most common, the group that you're going to see the most are those first three. So f prime of x, right? So we have that above. So dy dx. So the reason that we have that dy dx is we know typical slope is delta y over delta x, right? And if delta x is small enough, we say it's about equal to dy dx, right? But specifically, dy dx is when that limit approaches 0, right? So the limit of delta x approaching 0, and then of that definition of the derivative from above. And so what is that definition again? So f of x plus delta x, which again, you're like, I don't know that I know what that means, but we'll see that in action here soon. Minus f of x over delta x. So we can write, instead of f prime, right? So we wrote f prime up here. We could just write dy dx as well. And so that notation there is just saying we're actually calculating the slope or derivative of the tangent, right? Or of the function. So slope of the tangent versus delta y over delta x. That's when we're talking about slope of secant. I'm going to abbreviate that. Okay, slope of the secant line. So dy dx for slope, and then f of x can often be replaced with y. So instead of just f prime of x, we can also talk about y prime of x as well. Okay. And then this little section right here, this d over dx. So this is used occasionally, this notation right here. And oftentimes we'll say something like, the derivative of f of x, and then with respect to x. Again, a little too early to talk too much about that component, but you'll get quite a bit of that next year. And then this one is very rare to see, this one right here. All right, so differentiability, okay? So when we use that word differentiability, what that means is, a function, can we evaluate the derivative? So when we talk about differentiability, we're talking about, okay, here's my derivative. Am I allowed to evaluate that derivative? And so you can determine it by actually looking at the equation, but you can also determine it looking at your graph as well. So again, when we talk about differentiability, when we're talking about that, we're asking, can we evaluate the derivative? And if we can evaluate the derivative, then we say it is differentiable there. And if we cannot, it is said to be not differentiable, okay? So you could definitely identify whether something is differentiable by just looking at the equation. So for example, let's say that I tell you the derivative is equal to, so I'm going to do f prime of x, right? So that notation, f prime of x means I've found a derivative. And so let's say we found that derivative and it was something like x divided by x plus 2. And if I asked you, is this function differentiable at x equals negative 2, you would say no, right? It is not differentiable. And why is that? So I'm abbreviating differentiable. Because we cannot evaluate the derivative at negative 2, right? That would be undefined. We would be dividing by 0. So when we say is something differentiable, it doesn't mean can we find the derivative, can we not find the derivative? We can always find a derivative. What we can't always do is evaluate that derivative. And there's a lot of different reasons, okay? So we're going to be mostly working with it in terms of equations, in terms of graphs, not equations. So we won't be seeing anything, like here's this equation, what is it differentiable or not? We'll be looking at graphs. So when we take a look at that piece and we're saying, is it differentiable or not? And so what our pictures would look like, so we have, if something is discontinuous. So let's take a look at let me get into pen mode. So what would discontinuous look like? So maybe that is kind of like our absolute value graphs that we've done in the past. So like maybe you have, a graph that does something like this. And so we would say that this is not differentiable. We'll call this f of x. So f is not differentiable at x equals 0 because it's discontinuous there, right? So there's a split in the graph. So what would a sharp turn look like? So this one, a sharp turn. Perhaps you have something that looks like that. So that would be a sharp turn, and we'll call this one g of x. And let's say that was at 1. So we would say g is not differentiable at x equals 1. And that's because there is a sharp turn there. So different ways to look at it is like, because you have that one-sided limit, they have to agree. Do you remember that? So the left limit has to agree with the right limit in order for the limit to exist. So if I compare my slopes here, so if I'm approaching from the left, so if I look at this left side right here, so I'm looking at that, I can see that what kind of slope I have. I don't know the value of that slope, right? But I know the slope maybe is some value that's got to be positive, right? Whatever that might be. So I know the slope is positive. And then if I look at the other side, so let's take a look at this side right here. The slope of that particular guy is a negative, right? Because it's going down, so the slope would be negative. So I know if I approach from the left and I approach from the right, I have a positive versus a negative. So what's happening at that guy? Well, is it positive? Is it negative? What would be that slope? And so we can't say. So the one-sided derivatives don't agree. And there's other reasons, but that's one way to kind of think about that. So at sharp turns, our graph is not differentiable. And then our last idea here, vertical tangent. So let's take a look at that. So vertical tangents. This one's a little tougher to draw, for me anyways, is let's say that I have a graph that's like that, and then it gets really steep right there. And I look right here, maybe at that point, we'll say that's at x equals 1 as well. Again, I didn't draw that very well, but let's say that for whatever reason, this became so steep that the tangent line became vertical there. And so then we know a vertical line has a slope that is undefined. And so then we would say that h is not differentiable at x equals 1, and that would be because I would have a vertical tangent. Okay, so not a vertical asymptote, but a vertical tangent. All right, so let's go on and do some examples here so we can kind of figure out like how is this supposed to happen. Okay, so for this first part, so this is just kind of a reminder of what a tangent line looks like, or an equation of a line, sorry. So this is our point slope form, and you can actually use any form, but this is the form that we tend to use. So our point slope form, and then we will be looking for equations of tangent lines, and we'll be, when we do equation of a tangent line, this is the form we'll be putting it into. So our point, our ordered pair, has to be a point on the line, right? And then in this case, because it's a point of tangency, it's a point on our function. But it is also our point of tangency, right? So it's a point on the line as well. And that would be the ordered pair x1, y1. So that would be x1 and y1, right? So the point on the function, point on the tangent line, our point of tangency, all of those have to be the same exact point, right? And that would be the ordered pair x1, y1. And then our slope is going to be that m value. So this is our slope right here. All right, so let's go ahead and practice just like creating equations of lines. So for example 1, we want to find that equation of that tangent line. And again, we're going to be using y minus y1, and then equals m times x minus x1. So we want to use that point of tangency. So that's going to be the first thing that we're going to take a look at. So that would be this guy right here. So then we know that that is our x1 and our y1, right? So our ordered pair that we're going to be working with for x1 and y1 is negative 5, 2. And so then the only other thing we need to find is our slope. So let's go ahead and do that. And so to find our slope, we're going to just be doing like delta y over delta x. So we find those distances just by subtracting. So that means I'm going to be going up and over some amount, right? So I'm going to go up some amount and over some amount, oops, to that point there. And then how much I go up is my delta y, and how much I go over is my delta x. So I'm just going to be subtracting my y values in order to do that, right? And it doesn't matter which way I subtract. I know some people kind of get hung up on subtracting a particular way. Just as long as you're subtracting the same way for both, then you're fine. So I'm going to take my higher y value, so 6, and then I'm going to subtract 2 from it. So 6 minus 2, and then all over delta x. So then I'm going to take my delta x value. So I'm going to start with negative 3 because I started with 6 last time, and then subtract my other x value, which is negative 5. And so then that slope would be 4 over, I have a double negative here. So 5 minus 3, which is 2, so my slope would be 2. And so then now I know enough information, right? So I have my ordered pair and I have my slope, and then now I can write my equation. So I would do y minus y1, so that's this guy right here, which is 2, and then my slope, which we found earlier there, and then x minus x1, which was negative 5. And then that double negative, of course, could be a positive. So that would be the equation of that tangent line, right? So that's just a review again from your kind of Math 1 days. All right, and let's do one more here just to make sure. So you might want to press pause and try to do example 2 on your own, and then just kind of flash forward and see if you got the same thing I did, okay? All right, so I'm going to go ahead and call my point of tangency right here, so 4, 8. And so that would be my x1 and y1 value. And then I need to find my slope, so delta y over delta x. So I'm going to go ahead and take my higher y value and subtract my smaller. Again, I can go the other way, it doesn't matter, right, as long as I'm consistent. And then because I started with 8, that means I'm going to start with 4, the partnered x, and then subtract the other x value, which is 6. So that would give me 8 minus 6, which is 2, and then over negative 2. So then my slope, or m, would be equal to negative 1. So then again, I'm going to refer back to this guy right here to write my equation, and I'm going to do that up here. So that's going to be y minus my value for y, which was 8, and then equal to my slope, which was negative 1, or negative, right, either way, and then x minus my value for x, which was 4. And that would be my equation of my tangent line. Okay? So not so shabby, right? Not the worst thing in the world. Okay. So now here comes the fun stuff. Okay, so I'm going to zoom in here just so I can kind of do these problems. So we are going to want to write pretty small because it's kind of a doozy. It is kind of a doozy. All right, so this is where that whole definition of the derivative comes in, okay? So this is important, right? So we've got this definition of the derivative. So that is f prime of x, right? F prime of x. So when we find a derivative, what we are finding is a formula to find the slope of any tangent line for that particular function. So that is kind of really key there, okay? So that is a super important idea that we just said. So one more time. So when we find a derivative function, this whole f prime of x, so what we're finding when we do that, and I'm going to like steal some space up here because I know I need every inch down below. So whenever we find that derivative, a derivative is going to create an equation or a rule or a formula, like however you want to call it, that finds the slope of a tangent. And it would be any tangent on f of x or g of x, whichever one it is, okay? So again, what are we finding? Every time we find a derivative, we have to find what we're finding is a rule or an equation or a formula, like whatever word is going to stick in your brain, that will find us the slope of any tangent on f of x. So if we look at the problems above on 1 and 2, we were given 2 points, right? So we had 2 points to work with, so finding slope, easy breezy. But then that would kind of defeat the point of having a derivative. If we always were given 2 points, why do I need a derivative? Well, it's because you're never going to be given 2 points. Or I shouldn't say never, but rarely. So somehow we have to find the slope of a line given 1 point. Well, that's darn near impossible, right? Up to now. And that's what this whole derivative function does for us. So it's super cool in that we create this rule, and then given this rule, then we can go about finding the slope of any line that we have that is tangent to my function. And I only need 1 point. I don't have to like find a second point. And so that's like the cool piece of it, okay? All right, so here we go. So we're finding a derivative. And remember, when we find that derivative, we are going to be creating a rule to find the slope of any tangent line, okay? All right, so I'm going to just jot this down just to kind of make sure I say that again one more time. Okay, so don't draw this picture on your notes. This is just me chattering away. So 2x squared plus x plus minus 1, like whatever that looks like, we know it's a parabola located somewhere. And so what we're going to do is I want, eventually, not on example 3 or 4, is I want you to find the equation of a tangent line of that particular function at x is equal to, say, 7. Well, then that means I need to create a rule. So that means we need to know what f prime of x is, like whatever that might be, like maybe it's x plus 3. And then if I want to find slope at 7, I would just have to put 7 in here, and I would say, oh, the slope is 10, like easy breezy. Well, what if I was over here and I was like, okay, well, find this slope over here at x equals -1. Easy breezy. Plug -1 into there. So that slope, when I plug in -1, would be -1 plus 3, which is 2. What if I wanted the slope over here at, say, x equals -5? Well, then I would just take -5, plug it into there, and then I would find my slope, okay? So that's what we're looking for, right? So we're trying to find some sort of rule like x plus 3 or whatever it might be that will help us find the slope for any point on that particular function. All right, so here we go. All right, so the first thing I do is I copy that formula that's highlighted in yellow. Okay, so I'm going to be writing pretty small here to make sure I can get this to fit in. So we've got the limit. I'm just copying that formula. So the limit as delta x approaches 0. And then I bracket off each section separately, okay? So I'm going to take this f of x plus delta x, this guy right here, and I'm going to find what that is. So all that is saying is you're going to make this equation right here a whole lot messier than it is, because you are going to have to take every single x, so every single x here, so that's these two guys right here, and you are going to have to replace it with x plus delta x, because that's what that's saying, right? So you have to take every single x and replace it with x plus delta x. Okay, so let's go ahead and do that, right? Okay, so what am I going to do? I'm going to take every x I see right here, and I'm going to replace it with x plus delta x, because that's what this notation is telling us to do. And I'm going to bracket that off. So I have a bracket, and then I have 2, replace x with x plus delta x, and then it's still squared, plus replace the x with x plus delta x, and then minus 1. Okay? So all I've done is this part right here, and I did it by taking every x and replacing it with x plus delta x, okay? So now I'm going to move on to the next section. So then the next section says now we have to subtract f of x. So now I have to subtract f of x. Well, here's f of x right there. And then what else is there? We have to divide by delta x. So divided by delta x. Okay. All right. So one more time. Okay, just in case we lost that. Okay, so let me do a little erasing here so I can repoint. So let me get rid of this guy right here. Get rid of that there. Okay. So the first thing that I'm taking a look at is this section here. So f of x plus delta x. So this is the same exact basic function, right? So all I'm doing is I'm taking every x that's up here and replacing it with x plus delta x, right? All of those x's swapped out for x plus delta x. And then what did I do next? So then the next thing I did was I subtracted f of x. So I subtracted f of x, which is just the same original function one more time. Okay. All right. So now I just have to simplify it, right? Easier said than done, I will tell you that. So do take your time. Don't rush through the algebra of this because you will make little mistakes along the way if you don't take your time. So make sure you're copying that limit down. So squared meaning I have two of those, right? So I'm going to write x plus delta x twice because that's what squared means. And then I don't need the parentheses on that second group. And then I'm going to go ahead and distribute that negative in. Okay. So the x plus delta x minus 1 is exactly the same. That didn't change. And then all I did was write this piece out twice. Okay, so I'm going to go ahead and do a little distributing and combine. So I'm just going to copy down that limit again one more time. And then I know it's going to be all over delta x. So I'm going to go ahead and distribute this out. So x times itself, and then x times delta x. And then delta x times x. And then delta x times itself. Okay. So that was just FOILing, yeah? All right, and then I'm going to do a little canceling here because I see I have a negative x and a positive x. I have a negative 1 and a positive 1. So then I still have a delta x and a negative 2x squared. Okay, so this would be a good time to go ahead and press pause and then maybe recap that beginning step or go ahead and distribute combine like terms and try to finish simplifying that fraction. So if you think you have a pretty good algebra base, go ahead and distribute, combine like terms, and simplify. And then forward to see if you got the same thing. So now I'm going to go ahead and distribute in that 2x squared. And then copy that section over. And then all over delta x. Okay, so go ahead and let's combine like terms. So I see that the 2x squared and negative 2x squared cancel. And it looks like I can go ahead and combine these guys right here. So let's go ahead and do that. So then I'm going to have the limit, right? That doesn't go away. So I'll have 4x delta x, and then plus 2 delta x squared plus delta x all over delta x. I'm just about finished. The never-ending problem. So I've got that all simplified, all my terms combined. So I'm going to go ahead and factor out. So in the numerator, I'm going to go ahead and do a GCF. And I see that as far as that GCF goes, they all have a delta x common. So I'm going to go ahead and factor that out, right? So I'm going to factor out a delta x. So for this first term, that leaves me with the 4x. And then this middle term leaves me with 2, and then delta x to the power of 1, right, because it's squared, so one of them will divide out. And then when I divide delta x out of itself, that leaves me with a 1 behind, and then all over delta x. And then the delta x's cancel. And so then I have the limit as delta x approaches 0 of 4x plus 2 delta x plus 1. And so then now I actually have to let delta x approach 0. So the only delta x remaining is this one right here. So if it approaches 0, it means it's going to be equal to 0 there. So then the only thing I'm left with is 4x plus 1. So then therefore my derivative, remember that's what we were looking for, is 4x plus 1. Okay. So what that means is if I asked you to find the slope of the tangent line for that original parabola problem, you would just use the equation 4x plus 1, the derivative. And so like what's the slope at x equals 3? You would just evaluate it at 3. So 4 times 3 is 12 plus 1 is 13. Okay. So again, what did we just find? We found the derivative, which is our rule or equation that will find the slope of any tangent line for the original function you were working with. Okay? All right, so those are a lot, right? Those are a lot. So you may want to press pause and then on a piece of scratch paper, try to do example 3 over again on your own and see if you get that 4x plus 1, okay? Because it is a lot of algebra, a lot of attention to detail, and certainly trying it one more time independently is about the best thing you could do for yourself to get through it, okay? All right, so let's go ahead and do example 4. We're going to do it the same exact way. And so give yourself some room here because it's gonna take a lot, right? So a limit as delta x approaches 0. So again, remember the very first thing that we're gonna do is we're gonna find f of x plus delta x. And so we do that, okay, by bracketing it off, and then anywhere we see an x, we're gonna swap it out for x plus delta x. And replace that other x with x plus delta x. Okay, so that's all we've done so far. Okay, so we took the x here and the x here and replaced it with x plus delta x. So we've only done this section right here. All right, and let me close off that bracket. And now I have to go minus, so minus f of x. So f of x meaning original. So this is my original. So then I'm going to subtract that. And then all over delta x, so all over delta x. Okay? All right, so one more time because I know this can be a lot. So let me erase this part right here. Okay, so the way to kind of look at this, okay, to kind of help you out here. Uh-oh, it's frozen. There we go. So I call this one kind of like my messy side. So this is like my messy or altered function, and then this one is my original, right? So messy or altered, you know, whichever way is fun for you, okay? So this is the original function I have in its altered form. How did we alter it? Replaced x with x plus delta x. And then this is always my original. So we take the altered minus the original all over delta x. And then we get the joys of simplifying, okay? So here comes that joy. So first thing I'm going to do is go ahead and distribute in that 3 just to kind of get the ball rolling for that. Distribute it in. And then minus 5. And then I definitely don't need those parentheses in that denominator, right? Because there's nothing to multiply through. And then minus my original function, which was 3x minus 5 over x plus 1. And then all over delta x. Okay? All right. And so from there, lots of different ways to simplify this. Like you might have like your own favorite way to simplify complex fractions, whichever way you want to do. So I'm going to do that by multiplying by 1, right, an altered form of 1, to simplify. So I'm going to multiply the numerator and the denominator of my two denominators, okay? So all I did was take this denominator, and combine them, and I'm going to multiply that to the numerator and the denominator. Okay, so we're going to go ahead and distribute. So I'm going to take both of those and distribute to the first fraction. So when I do that, this will cancel, right? And this one will cancel. And so then the only thing I will be left with is the 3x, right, plus 3 delta x minus 5, that original numerator, and then the one that didn't cancel, which was x plus 1. Okay. All right, so now I have to take those same original 2, right? So those same original 2. So I'm just going to kind of erase this right here. And then let me write that back in. And then now I'm going to take those and distribute to this fraction. And when I do that, x plus 1 will cancel, leaving me this numerator and that factor. And it's a subtraction, so don't forget your subtraction. And then all over delta x. Okay? All right, so you guessed it. We got to distribute and combine like terms. So this would be a good time to press pause and you guys try to distribute it out. See if you get the same thing I do, like once you get it like simplified and combined. So I'm just going to go ahead and distribute the 3x into x plus 1. And then the 3 delta x into both of those terms. And then distribute in the negative 5. Okay. All right. And then now I'm going to distribute the second pair. So I'm going to distribute 3x in. And I'm going to keep it grouped because I know I have that subtraction to contend with. So I'm going to keep it grouped for the time being. So that will give me 3x squared plus 3x delta x. And then plus 3x. Getting really tight here, huh? Okay, and then the negative 5, you may have to go into a second line as I'm branching farther and farther to the right, way off the page. All right, so negative 5x, and then minus 5 delta x, and then finally negative 5 times 1 is negative 5. All right, and then this is all over delta x. Okay, so now I'm going to go ahead and distribute this negative in, and then also do a little combining as I go as well. Okay, all right, so I have the limit as delta x approaches 0. And let's see, what can I combine here? So it looks like I can combine a 3x and a negative 5x, and that is about it. So that is not much. So that would give me 3x squared minus 2x, and then I have a 3x delta x. 3 delta x and a negative 5, right? So attention to detail, super important because there's a lot of things you're looking at and you're hoping not to mess up on something simple and then like not be able to finish the problem. All right, so now let's go ahead and distribute that negative in. So that gives me a negative 3x squared, negative 3x delta x. These two will combine here, so that'll be negative 2x, but that negative coming in will make it positive. And then these will just copy down because nothing will combine. Oops, don't forget to distribute the negative. And that's a delta. All over delta x. Okay, so we're getting there. Hold on, like, right? Stay with me, people, stay with me. All right, so here we go. So let's combine like terms. So this is the lovely part. 3x squared and negative 3x squared cancel. Negative 2x, positive 2x cancel. Negative 5, positive 5 combine to 0 as well. 3x delta x and negative 3x delta x combined to 0. So the only thing that doesn't cancel, 3 and 5 delta x. So yay, we don't have to write out a million things anymore. Isn't that wonderful? So many things canceled. So then when I add these two guys together, I will get 8 of them, right? I will get 8 delta x's and then over delta x. And then I just realized, but I do not want to redo this problem, is I completely forgot about this guy right here. Like, so this right here should be down with all of these. Oopsie daisy. You might have been going, where the heck did that go? I made a mistake, but I don't want to redo it. So I am just going to quickly copy it down and pretend it was always there. Oops-y daisy. Sorry about that. So again, we're pretending. I did not forget that, even though I really did. Okay, so, because that didn't disappear. That did not disappear. That is still there. All right, so here we go. So then my delta x canceled. And so then I would just have an 8. And so really, like, if that had not been there, I would have been like, it's 8? Like, it's always 8? Isn't that weird? Like, that would be weird. And, like, you know, it can happen. Don't get me wrong. And you'll see that very often. But that should have been, like, that's what triggered it for me. I was like, wait, I'm only going to be left with 8. Something's kind of weird. All right, so my delta x is canceled, and then now I need to, any remaining delta x that did not cancel needs to turn into 0. That would be this one right here. And so then I would have my answer of 8 in the numerator, and then I have x plus 1, and I have another x plus 1, so squared. So therefore, my derivative would be 8 over x plus 1 squared. And again, what is a derivative? A derivative is the rule or the equation that will calculate any slope of any tangent line provided it's differentiable. So for example, this would be not differentiable at -1, right? At -1. Okay. Whew. So much. Okay, so here we go. 2 more examples. And example 5 is not that bad. Okay. So you may want to press pause, go get a snack, and come back, though, because that was kind of exhausting, right? Okay, so here we go. Example 5. So for the following function, identify any values of x where the slope function would not exist. So that part A is that whole, like, not differentiable part, right? So where the slope function would not exist, that would be that piece where we are saying it is not differentiable. Right? Not differentiable. And let me recap that for you. So something is not differentiable, right? Meaning we cannot evaluate the derivative. And there was a few of them, right? So it might be discontinuous, so there would be a split. There might be a sharp turn, and so that would be like somewhere like right here, right? Where it's a steep point. Or where it looks like it might have a vertical tangent where it gets really steep on the function, okay? So that's what we're looking for. So for part A, the slope function would not exist at a sharp turn. So that would be right here at x equals 1, right? So we would say that the derivative here would not exist. So dy over dx, that's another way to write f prime, does not exist there. Okay, so that would be at x is equal to 1. Not differentiable because I have a sharp turn. Okay, all right, so the derivative, right, we can calculate the derivative over the entire function, we just can't evaluate it there. All right, and then for part B, so part B, they're asking us to find values of x where the slope function would be 0. So we know we have a slope function that is 0. So if the slope is 0, that means we have a horizontal line, right? We have a horizontal tangent line. So if I take a look at this, I would look to see, okay, where would I have a horizontal tangent line? So I'm finding those points of tangency. So like, let's say I randomly pick a point here and I drew a line through it. That is definitely not horizontal, right? So that would not be one, okay? So what if I pick, say, a point right here? So let's say I pick that point and I drew a tangent line there. Definitely not horizontal, so that would not be one either, okay? What about right here? What if I drew it right there? That would be horizontal. So that would be where the derivative, so dy dx, remember, is another one of those notations for derivative, as well as f prime. So that would be where the slope would be 0, right? So for part B, it looks like we have a place at x equals -2, right? So I'm going to go ahead and give you a minute. So there's one more point that has a horizontal slope. And there's also an interval that has a horizontal slope. So see if you can figure that out, okay? So press pause, see if you can figure that out. Okay, so the other place where you have a horizontal tangent, point-wise, is right there, right? There's another place, okay? So we have a horizontal tangent at -2. We also have it at x equals 0. And then there's one more, right? One more. And this one was a interval, right? So interval. And that would be everywhere over here, right? So no matter where I drew that point, I would have that kind of collinear tangent line. So that would be one that, is on top of the other one. And so that one starts at 1. So it starts at 1, but open interval because it's not differentiable at 1. And then goes to infinity. All right, and let's take a look at C. So C is asking us to identify the values of x where the slope function generates positive values. So we're looking for where we would have positive tangent lines or positive slopes. So if I take a look at the graph here, and let's say I drew a random point right here, that would have a positive slope, right? Yeah. And right here as well, another section where it's positive. So we would say that all of these pieces right here, so everything on this side right here, where the function is increasing, right? Kind of making a mess of that. So I'm going to fix that and not make it so messy looking. Okay, so I would say every section right here, what's going on? There we go. So every section right here, or any tangent line on this point of the graph, is where we would have positive slopes. And that's because as I move from left to right, my graph is going uphill, increasing. And so then I would say that my slope is positive there, and then that's going to be on an interval, right? So I'm going to use that element notation. So x is an element of, and then it's starting from negative infinity until I get to this section right here, which is at -2. And then again, not equal, because that's where it's 0. And then there's one more section. So one more section where we are increasing, which is a clue to where the slope would be positive. And that would be this section right here, right? No matter where I drew a tangent line, it would be going uphill. So that would be one more place. And so then that would be starting at 0 and going until we get to 1. All right, last one is where do we have negative values? Well, there's only one part of the whole graph that we haven't even referred to, so that's probably where it might be negative. And so that would be this like kind of little connecting point right here. And so that's everywhere we're going downhill. All those slopes are negative because we're going downhill. And so again, I'm using that element notation. So x would be an element of the interval from -2 to 0. And again, we're using parentheses because at -2 is actually where it's 0. And then at 0, it's actually where it's 0 as well, not negative. Okay? All right. So again, this might be one of those problems where you press pause, go back and try to redo it because there is a lot of information contained in that one particular problem. Okay? All right. So let's go ahead and do the last one here. So this one here. So this should be a little familiar, right? So they're saying that the slope function, find the slope function via the limit process. So that would be this guy right here. So we're looking for the derivative, right? Isn't that the definition of the derivative? The only thing different is we're changing, instead of delta x's, we're using h's. So we're going to do that first because there's more to this problem, but it says to find that slope function first via the limit process. So let's go ahead and do that. Okay. All right, so we're going to use h's instead of delta x. So we have the limit as h approaches 0. So we're going to have the altered minus the original, right? So altered minus original. So we're going to take this guy right here, and we're going to alter it, and we alter it by replacing x with x plus h. So instead of delta x plus 3, it'll be x plus h, and then plus 3. Okay, so that x right here gets replaced with x plus h. Okay, so there's the altered, and now minus the original, so x plus 3, and then all over h according to that equation, right? So altered minus original all over delta x usually, but in this case we're using h's. So you reviewed in 11.1 how to work with these types of problems, and that's when you work with a conjugate, right? And so you're going to multiply the top and the bottom by the conjugate. So instead of subtracting that square root of x plus 3, you're going to actually add it. And whatever you do to the top, you're going to do to the bottom. And I'm going to make sure I remember that that bottom one is there and not forget it, okay? All right, so we still have that limit as h approaches 0. And then because we are using conjugates, we love them. They're fabulous. When I multiply those two together, that will just give me x plus h plus 3, because that squared will cancel that root. And then I don't have to do the outer and the inner because they are conjugates, and that will always cancel. So then when I multiply the last terms together, I'm going to have subtract and then x plus 3. And I'm going to keep that x plus 3 grouped because I know I need to distribute that negative. And then in the denominator, I still have h, and then those two guys there. Yay, I did not forget. Okay, and then I'm going to go ahead and distribute in that negative. And then I still have my denominator. That looks exactly the same. And then I'm going to simplify. So let's see, the x and negative x cancel, the 3 and negative 3 cancel. And so these h's will as well, right? Now that there's only the h left on top. So I have the limit as h approaches 0. And when those h's cancel, that will leave a 1 behind. And so now the only thing left to do is any h's remaining, I need to replace as 0. So then I would have left a 1 over root x plus 3 twice. So that would be I have 2 root x plus 3's. So again, they're saying our slope function, and they're using that m of x notation, but I could use like f prime of x, dy dx, that whole thing, but I'm going to use the notation they're requesting. So 1 over 2 root x plus 3. So that's the first part. Okay. And the last part they're asking for is to write the equation of the tangent line at the specified value. So for us, that specified value is at x equals 1. And then a reminder of your tangent line, y minus y1 is equal to m times x minus x1. So we have x is equal to 1. So now to find the slope, we're just going to replace x with 1. And then 1 plus 3 is 4, square root of 4 is 2, 2 times 2 is 4, so this would be 1/4. So I have slope, I have the x, the only thing I'm missing is that y value. So in order for me to find y, I need to like figure out, okay, wait, how do I find y again if I know x? So like this is like going back to your math 1 days. So you know from the original problem, so we'll go right here. And we know f of x is the same thing as y, right? We use it often. So we know y is equal to root x plus 3. So then all I have to do is substitute in x for 1, or replace x with 1. So that would be 1 plus 3. And then the square root of 4 is 2. So y equals 2. So now with all of that bit of information, I can now write my equation of my tangent line. So again, what am I going to be using? I know I have my ordered pair here, x equals 1, y equals 2. So that ordered pair is 1, 2. And then I know my slope right here, my slope, which is 1/4. So that equation would be y minus my value for y, which was 2. And then equals m. And then x minus my value for x, which was 1. And there's the second part to the second answer to this particular problem. All right, there we go. And that is the end of that one.